Biology teacher was talking about too.
Yeah.
So that means probably you guys should maybe listen or something.
Huh?
Where I ended last time was we developed the picture of orbitals in an atom. We used 3 of the quantum numbers that come from Schrödinger's equation. N, L, and M sub L, principal quantum number, the angular momentum, or as a useful quantum number, and the magnetic quantum number. And I gave you the rules for each of those. N can be 1, 2, 3, or any positive integer. I said L can be 0, any integer up from 0 up to 1 minus n. And I said that M sub L can be any integer from minus L through 0 to positive 2. And I also told you what each of those describes for you. N, the principal quantum number, describes the principal energy level, where you can think about that 2 ways. They're really equivalent. The energy of the electron in that shell, N describes the shell, which is pretty much governed by the distance from the nucleus that electron can extend. And the farther away it can go, the higher its energy. There's a lot of stuff here, but I'm just reviewing what we did. Is that okay so far? That's N. L describes the shape of the region of space where there's a high probability of finding an electron, 90%. That's called the orbital. Well, it's called the subshell. And in each subshell described by L, there can be 1 or more orbitals, and they each have that shape described by L. And the number of orbitals in any subshell is described by the number, or determined by the number of values that M sub L can have. Is stuff familiar? This is important stuff. So what we have now is we're starting to build up anyway, a picture of the regions of space, these orbitals, where electrons can reside in that. And the last thing I did was I described for you the relative energies of electrons when they go into these orbitals. Remember the list of the S, 1s, 2s, 3s, 4s? Remember that, with the arrows going through them diagonally? That was a sort of a mnemonic device for remembering or figuring out which orbitals have lower energies and which orbitals have higher energies. So the first one, 1s, that's the lowest energy subshell, actually. And then 2s, and then 2p, and so on. The reason that's important, yes?
So 7F would have the highest?
Of the ones that we wrote down there.
Okay.
We won't get to that. We're not going to worry in this class too much about the lanthanides and the actinides. We're going to stick up to the transition metals and the things. So what we're going to do now is we're going to start taking electrons and putting them into these orbitals, in these subshells, in these principal energy levels. And to do that, we have to know a few rules. So I'm going to talk about the rules that determine where these electrons go and how many can go into each orbital. There's going to be the Pauli exclusion principle, the Aufthal principle, and Punn's rule. So that's why I'm about to describe these for you. So tell you what they are.
I should fix the lighting. No, it's good.
And so I believe I described M-SVES for you last time. Does that look familiar? The spin quantum number. What's the rule for M-SVES? Do you guys know that one?
hat or negative hat?
Yeah, and can only have two values, right? And they're plus or minus a half, but that really doesn't matter, it's just that they can have two values, that's the point. So, what Pauly said, Wolfgang Pauli, is that in a given atom, you can never have two electrons that have all four quantum numbers identical to each other. That's the Pauli exclusion. What that means as a practical matter for us is that in any specific orbital, there can be no more than two electrons. The reason is this. If you pick a value of n, and I'll say 3, and then then pick a value for L. Let me ask you this. If n is equal to 3, what values can L have? 0, 1, and 2. 0 up to 1 less than n. So I don't know, let's say that L equals 2. What's the name for an L equals 2 subshell? Right?
D.
0, everybody forgets the 0, right? It's SPD 012. Okay. So L equals 2 is a D subshell. We already said n equals 3. So it's a 3D subshell. Let me ask you this. In a 3D subshell, how many orbitals are there?
5.
5. 10, 5, 7. Remember, okay, it's good to refresh your memories because you have to be able to do this pretty quickly. So what determines how many orbitals there are in a given subshell is how many values of m sub L there are. And remember, the rule for m sub L is negative L through 0 up to positive L, right? So we said L equals 2. That means m sub L can be minus 2, minus 1, 0, 1, or 2. It has 5 values, so that means there are 5 orbitals in that subshell. But we're not to the electrons yet. Now, the Pauli exclusion rule. We've picked n, we've picked L, right? And there are 5 orbitals, right? So if we pick one of these orbitals, it doesn't matter which. We don't care what the actual value of m sub L is, just that there are 5 values. We pick one of those orbitals. What the Pauli exclusion rule has said that we've picked one of those values of m sub L, and now we only have one quantum number left. Okay, so everything's the same. N, L, m sub L. M sub S can't be the same, or else we violate the Pauli exclusion rule. It has to be different, right? And there are only 2 values for m sub S, plus half and minus half. It has 2 values. And what that means is that in that one orbital where we picked N, L, and m sub L, because we still have m sub S, we can put 2 electrons in there. They'd have to have different values for m sub S. But once we do that, we can't put any more electrons in. Did you guys follow all that? when two electrons have different values of s, we say they have different spins. So that's the Pauli exclusion rule. We have two more to talk about, the Allen-Bell principle and Flynn's rule. And then we'll be able to put electrons into these orbits. Any questions on the Pauli exclusion rule?
So given M N L which is 3, 2,
Just one of the spins. No. There are five of these orbitals. And we just picked that random one.
Was that the two electrons?
Pick an orbital.
3D speed equal to
It's what tells us which orientation that the orbital is at. So we don't care. It could be -2, -1, 0, 1, or 2. Just randomly reach over and pick one of those. Now we have one orbital.
and in this situation, we're always looking
Well, we're not solving for anything. All I'm doing is I'm describing for you the Pauli exclusion rule. I'm trying to spell out for you that as a practical matter, the way you're going to use the Pauli exclusion rule is that you're going to realize that it tells you that no orbital can have more than 2 electrons. That's it. I'm trying to say why that is.
How do you figure out what the spin is?
You don't care. I mean, we could do an experiment. All we care about is that it can only have 2 values, up or down, let's say. And that's what determines how many electrons can be in that orbital. It's 2 at most. Notice I'm saying at most. There could be 0 electrons in an orbital, or 1, or 2, but those are the only ones.
So it's basically saying that only one orbital can only have 2
At
electrons.
most. That's
At
right.
most.
That's
Okay.
right. That's all it's saying.
No, that makes sense. Okay.
Okay? Next, the outbound.
See, that's why in 3D there's 5 slots. There's like all 10.
Right.
It's spinning. This thing. And the spin's represented by like dashes. If the first electron spins outwards, the other one spins in
How do you say that?
Yeah, one spins this way. and
I
one
say
spins
alpha
that way.
bound. I don't know if that's right or not.
That's
Say how
fair.
you want it. Sounds right. There you
That
go.
sounds.
Hofbrau?
Have you been to that place downtown called Hofbrau?
My decadent youth, yeah.
Yeah.
Is that so? Shut up.
This is basically what the alpha principle says. The electrons in an atom will be in the lowest, or reside in the lowest energy orbital that has room. Now that we know about the Pauli exclusion rule, we know that it has room if there's less than 2 electrons in it. But if there's 2 electrons in an orbital, then there's no room for any more. And we also know about the relative energies. That's that diagram with the arrows, that mnemonic device that I showed you guys last time. 1s is lower in energy than 2s. These are the subshells, the orbitals in these subshells. The 1s orbital, the 1s subshell is lower in energy than the 2s orbital in the 2s subshell, which is lower in energy than the 3 2p orbitals in the 2p subshell, and so on. Does all that make sense? Finally, Flynn's rule.
There's so much rules on
No, it's the same on the rules. We had to go through these before we started doing the electron. The 3S, 3DS, and F2P, and all that stuff. And That's the next thing we're gonna do.
Yeah, if you want to play the game, you're on the rules.
I don't know the rules. I'll learn as I play. I don't work that way. I just want to go to sleep.
You just wake up.
Something has to be quiet.
And the pre-orbital has space for 3. Whoa, I see. Sweet.
Damn it. Yeah, erase it.
I know she's in the lab of flat on Tuesday. She's collecting the lab book. That's what means. We sent you to the state of office. We stayed until classes was on the spot.
Yeah.
She's collected on Wednesday. Because I'm not.
Yeah, good.
Looking at my conclusion, you see
So, when you have degenerate orbitals, degenerate means they have the same energy as each other. For instance, if you remember back to that, those arrows in the mnemonic device, the 1s subshell, then the 2s, and then we got to the 2p subshell. In any p subshell, such as a 2p subshell, how many orbitals are there?
There's
3, right?
SP1,
Okay.
SP2, SP3.
Those 3 2p orbitals, or any of the orbitals at the same end, have the same energy as each other. So they're degenerate. The energies are degenerate of those orbitals. They're degenerate orbitals. Okay. And that's the situation that I'm talking about here. You have degenerate orbitals at a p subshell, a d subshell, and an f subshell. So when you get to that situation, this is what Hundrel talks about. You have to put one electron into each of those degenerate orbitals before you start pairing them up. It also says that when you put that first electron into each of these orbitals, all those first electrons have to have the same spin. That means the same value of m sub s, which, and I'll show you how we describe it, but you can think about it as either pointing up or pointing down. It doesn't matter which, but they have to be the same, all pointing up or all pointing down. Then, if you have more electrons and you start pairing them up in those degenerate orbitals, now when the second electron goes in, it has to have the opposite spin as the first. That's the Pauling exclusion. Yes. So the question is, what are degenerate orbitals? They're orbitals that have the same energy as each other. And the orbitals that are degenerate are at any p subshell. All 3 of those orbitals are degenerate. At the d subshell, those 5 d orbitals are degenerate. And yeah, so.
Okay.
Yeah. You guys okay with that so far? Any questions? So we've got a bunch of rules now. We've built up to the point now where we can start putting electrons into these orbitals that we've described. So just to, yeah.
I have a question. When you had those values up there for n equals 3,
Yeah.
are you supposed to be able to determine the n sub L just based on that information, or is that not
Well,
enough?
once you know n, you can figure out what values L can have. And then we picked one of those values, Bill. And once you know what L can have,
And
you
it's
know
the
what
first
possible,
electron.
what value L has, you know what possible values M sub L can have.
Then F.
And then I just picked at random one of those values. So I used my favorite one. Picked an order.
Okay, so this
So-
would be the best thing for you to read when you do get home.
No more than 2 electrons in any given orbital. Electrons go into orbitals that have the lowest energy first, as long as there's
You
room.
have to read this.
And when we're putting electrons into degenerate orbitals, 1 electron in each, all with the same spin, before we start pairing them up with the opposite spin. That's basically those rules. So now,
But you don't even read it though.
the idea, For now, we are only talking about neutral atoms, atoms that have the same number of electrons as protons, no electron charge.
Remember that it's only 2 per orbital.
Man, time's going by so slow.
Yeah, what I did was I wrote down the Pauli says that in any atom, no more than 2 electrons can have. I mean, you
Just
can't
one
have
of
2
those
electrons
days where it's just
all
slow.
four particles the same. And then I showed you what that really meant for us, was that in a given orbital in a given atom, you can have those 2 electrons. That's really how we're going to use it. So let's pick an atom.
Carbon.
How about
Carbon. Carbon.
calcium?
Yeah, you gotta choose a hard one.
Boring? Okay, pick a better one. Pick a better one. They're all good.
Magnesium.
Zinc.
I don't want anything too complicated down the bottom yet.
Argon. How about argon?
Gallium.
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 How about copper? I heard copper.
I mean, that's a gallium.
So for now, we're going to use those arrows that I showed you, but real shortly, I'm going to show you how you don't have to write that.
It's 29.
You can just look at the periodic table and you get this information. But let's write it down real quickly.
Professional.
This
Got you on the move.
this would help greatly, like this diagram.
Yeah.
It lines up the whole periodic table with which
Oh, the camera's gonna fall onto it like that. Let's hold this part down. Oh my gosh. The hell did she stop at? 1, 2, 3.
So in a neutral atom
On
of copper,
4.
well, in an atom, any atom of copper, how many protons are there?
29.
29. No, you
29,
got
right? And you know that
So,
because the
so.
atomic number from the periodic table is 29.
It's not 29 neutral.
And so in a neutral atom of copper, how many electrons are there? 29. So what we're going to do is we're going to take 29 electrons and start putting them into these orbitals following the Pauli exclusion rule, the Aufbau principle, and Lenz's rule, until we run out of electrons. Now, so another way of writing, really, that
Is the
device
is line.
is to make, each line that I'm going to write represents a single orbital. So it's going to have a little bit more information. 1s. And in this diagram, energy increases as we go up. So after 1s, the next highest energy
2s.
2s.
And then 4.
After
We're skipping.
2s comes to 2p. How many lines should I write for the 2p? 3 left, right? Notice, okay, this is energy going up. Notice that 3 lines are at the same energy. That's because they're degenerate. Comes after 2p.
1.
1. After 3s,
3SP.
3p, right? And
Yes.
how many? 3. Every time it's a p subshell, there are 3 orbitals, 3 lines. What comes next?
3SP.
This has to be
right?
4D. It has to be 4D. It just has to be 4D.
1 line.
Then
After
it
4s,
has to be
Oh, you're already doing it?
Yeah.
5 lines, right? Everybody okay that there are 5 lines of the 3D subshell?
Uh-huh.
And I'll stop there because I know that that's all we're going to see. Okay?
Cheated.
Now, all we do is we start taking electrons and we put them in, the Aufbau principle says they go in the lowest energy orbital that has room. Pauli exclusion rule says
There's
that
40 slip.
there's only 2 can go into each orbital, but if we have 2 electrons in the same orbital, they have to have opposite spins. we're going to represent an electron with an arrow. And that arrow can either point up, point down. Spin up, spin down. Plus a half, minus a half for M sub S. Doesn't really matter which way. So we have 29 electrons, 29 arrows. We're going to start putting them in here. Lowest energy first. No more than 2 in an orbital. And if we do have 2 electrons in an orbital, one has to point up, one has to point down. So 1, 2, 3, 4, try to get to 29. Now, when we get to 2p, Kunz rule, we have to put 1 electron in each of these first. And whichever way that first electron points, the other two have to point in the same direction. So 2, 4, 5, 6, 7. Now we start carrying them up, opposite. 8, 9, 10, right? 11, 12. Once more, Kunz rule. 13, 14, 15, 16, 17, 18. Orbital diagrams, energy orbitals. Okay. I lost track. 2, 4, 6, 8, 10, 12, 14, 16, 18. Sorry. Track. 19, 20. You guys understanding what I'm doing?
Yes.
20. So now once more Kunz rule comes into play. 21, 22, 23, 24,
25, 26,
The last one should be
27,
27,
28.
29.
Yay!
Now, I shouldn't have picked copper because it's an exception, but this is the method. Okay? Did you guys understand everything I did there? We'll do a couple more. But now I can tell you about copper. It ends up that there are some exceptions. It ends up the lower you get in the periodic table and the transition elements, the more exceptions to the order of filling there are. And this is the second exception that we run into. It ends up, okay, and it's just because it's an exception, that it actually looks like this. Why?
There's another one.
Why? Yeah. Well, I can.
It's more stable.
In my way. Yeah, basically, yeah. Is that because it has more to do with energies? Okay, actually, Kevin's question brings up something that I should just tell you now. It ends up, when you're looking at electrons in orbitals and atoms, that there are certain configurations, certain ways of arranging the electrons that have a little bit of extra stability associated with it. One arrangement is with a half-full subshell. This is a half-full subshell, right? Another arrangement is a full subshell. This is a full subshell. So it ends up that with copper, a couple of things happen. Well, with all atoms, a couple of things happen. Well, as you get higher and higher in energy, as the orbitals extend farther and farther from the nucleus, they start getting closer and closer to each other in energy. So that's why as you get farther down in the periodic table, you get all these exceptions because the energy levels are so close to each other that any little thing can make one more stable than the other. And that's what's happening with copper. That little, it's not much. I mean, numerically, it's very, very small. But it's enough to where that the energy of this electron configuration is just a little bit lower than the energy of that first one that we wrote. And in nature, everything always, if left alone, ends up in the lowest energy state that it can be in. This is the lowest energy state for copper. Does that make sense to it? Kind of. What?
Questions?
Oh, question.
What was the other
Do
example?
dance.
Oh, well, there are many. Chromium is another exception. I'll give you guys, I'm going to ask you guys to basically memorize a few exceptions, and I'll tell you those in a moment. John.
Is this part of the reason why copper is such a good conductor?
It is, actually. Yeah, because it has that one electron there.
So any all of the exceptions are gonna be strong conductors.
Well, most metals actually are good conductors. of
Well,
heat
but
and
better
electricity.
than the.
Than other metals, yeah.
You just got planted.
Depends on how the exception ends up playing out. That unpaired electron there is one of the things that helps to do it.
I think I kind of missed how you word the 1s, the 2s, the 2p, the 3p, all those.
Were they, how I do.
How you got to those? Yeah.
Well, for now, I'm looking at this.
Right.
So, you go through
So
the arrows.
1s, right? 2s.
2p.
Oh,
God bless you.
So, yeah, to the 2s.
2p.
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 And then
Oh, okay.
after that,
That's good. When do you know how to stop?
See how it goes? After you get
Three
the minute
Ps.
arrow, go back up.
Go back. Okay, that's with the
How
zigzag.
do you know when to stop one arrow?
Okay.
you don't. You just need to know. You just need to know how far it's going to take for you to fill up the electron.
Oh.
And see, like you're gonna eventually.
This gets really awkward, okay? Writing out
And you can kind of probably gauge
an
it
orbital
just by looking
diagram
at
like this each
the
time.
like at some point.
Yeah, I
You'll
know.
So we have
There's
shorthand.
just one
how much
SP.
electrons it has. You know where it's going to stop.
You just write the names of the subshells,
I like him ball. You can take this in my nose.
and we use a superscript to describe how many electrons are in that orbital or that subshell. This has 2, so we write 1s2, not 1s squared, but 1s2, then
It has 2
2s2,
electrons.
2s2.
2p6, right? 3s2, 2p6, 4s1, 3d,
5, 4.
10, right? 2, 4, 6, 8, 10.
It's like 4 as 1 to 1 is right.
Yes, and this is the one time where it's the one you actually have to write. If it's a 0, then you don't write it. You don't even write the.
Oh yeah, and then you know, you just skip those.
This is
Yeah.
called the electron configuration.
No, you go to a noble class, you just go straight to the KR or whatever.
Yeah.
You s-
No, it's actually
It smells good.
What is that?
Electron configuration.
has to be
Is that what that smell is?
Oh.
Let's do some more examples. And then, I'll tell you a few things about the periodic table.
Let's do chromium. Chromium. Argon. Do argon.
Argon it is.
Just put, you know,
We should just do chromium.
Why is that one of the homework problems?
No.
I know, man. It's what I say homework problems.
You only ask homework problems and discussions.
I'll tell you this. The other one's probably sure.
We should just make
And I'm also going to have you guys remember.
We should just be able to do
left
hydrogen.
field.
Do hydrogen. Lexi, tell him, do hydrogen instead. Oh man, hydrogen or helium.
So the argon, in a neutral atom of argon, how many electrons are there?
18.
So we start at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
I should have chosen an odd number.
You guys, is that okay? You want that? Or the electron configuration would be 1s2, 2, 2p6,
6,
3s2,
SP.
6p6.
I think that's just bracket AR.
Yeah, no, I was thinking just bracket AR, that's it.
Cheater.
Looking to potassium.
No,
Another one, that one.
Can we do an odd number?
I want to do nitrogen.
I should have done fluorine instead.
It ends up, all we need is that many for nitrogen. So, how many electrons in nitrogen?
7.
What nitrogen?
7.
So, 1, 2, 3, 4. Now, following Ohm's rule, 5, 6, 7. Or the electron configuration. Can you guys tell me what the electron configuration is?
1s2, 2s2.
2p3. Not 6.
Okay, wait.
Yay, 2p3. You guys failed.
Wait. You can't say
One
anything
thing this
until
tells
two.
us is that there's one or more unpaired electrons in nitrogen. You know what I mean by unpaired? There's not a second one in the orbital. And we have a name for that. We call that, if there's at least one that's unpaired, we call that paramagnetic. If they're all paired, we call it diamagnetic.
Diamagnetic means they're pair. Paramagnetic means they're single.
The singles, yes.
That means they're single, they're not taken.
Yes.
That means you can do a lot of things to it.
Dun. I don't know.
What happens on Thursday? I want to know.
So this tells us that nitrogen would be paramagnetic, nitrogen atom. The result of an atom versus anything being paramagnetic is that if there's one or more unpaired electrons, remember when we were talking about the spin quantum number, I explained how an electron acts as if it's a negative charge that's spinning, and that creates a magnetic field perpendicular to its direction of spin, or it acts like a little magnet. So if we have two electrons that are paired, one of them spinning up, one of them spinning down, their magnetic fields will cancel out, right? And there's no overall magnetic field, and it acts like there's no magnet there. But if you have one or more that's not paired, there's going to be a magnetic field that's not canceled out, and it's going to act like a magnet. And so what that means is if we put that inside between the poles of a bigger magnet, right, it's going to feel that magnetic field. It's going to line up with the field of the external magnet. It's going to be affected by it. And we can see that. It ends up, we have to get to molecular orbital theory first, which is later. But when we do, we're going to talk about how oxygen, the oxygen molecule, I'm just doing single atoms here, but the oxygen molecule ends up being paramagnetic. And when you take liquid oxygen and you pour it between the poles of the strong magnet, you can see it's held there. It's held between the magnet. If you take something that's diamagnetic and you pour it between the poles of the magnet, it just goes straight through. So paramagnetic, diamagnetic, know what they mean, know how to predict if an atom is paramagnetic or diamagnetic based on its electron configuration.
So if it's diamagnetic, do they have a magnetic force with each other that cancels out overall, or
Does what have a magnetic force?
the electrons, like you're
They
saying?
cancel each other out. They're all paired up. Diamagnetic means they're all paired up. So each one that's spinning this way has one right next to it spinning this way. And this magnetic field exactly cancels this magnetic field. There is none.
So there's no magnetic field, but is there a magnetic force between the two electrons paired together, or no?
Magnetic force.
It's a dog.
Well, you're saying that it acts like magnetism when their spin directions are opposite, so they're like little magnets, right?
Yeah.
But do they have a magnetic force on each other, or?
Yeah, a little bit, yeah. And we're going to talk about the repulsive force a little bit. Good, so we have that. Now, all of this, is bulky and awkward, and we don't need it because we have the periodic table. It ends up, remember when they wrote down this periodic table, they arranged the atoms in order of increasing atomic number. Well, that's what it ends up being once you figure everything out. Increasing atomic number, which means increasing number of electrons in the neutral atom, which means as we go from one block to the next, going from left to right, top to bottom, we're putting one more arrow, one more electron into an orbital. We'll keep going up, right? Just like we did here. when I wrote down the orbital diagram, orbital diagram for nitrogen here, basically each time I put an arrow in, I was moving one block over in the periodic table. Does that make sense to you guys? So, use this one here. It's just a generic orbital diagram. And as the rules tell us that the first electron has to go here. That would be the electron configuration for hydrogen. I'm going to go one over. Next one is helium. That's this. That's 2. Then what comes after helium?
Lithium.
Lithium. So the next electron, that will be the electron configuration for lithium. 1s2, 2s1.
What makes, like for 1s, makes the first arrow go down, and then for 2s, the first arrow goes down?
Me. It's random is what I'm saying.
Oh,
It
it's
doesn't
random.
matter which
Oh,
direction.
okay.
I developed habits over the years. I usually write my first arrow down.
So
I don't
it
know
doesn't
why.
matter
Doesn't
which.
matter.
Okay.
The only thing that matters more is that they're off. If
Yeah.
there's 2
Okay.
there, they're opposite.
Because that's how I know arrows go down. So right away.
No, he just
So
copied.
lithium, and then beryllium. 1s2,
Your arrow shall be the same as
2s2. Are you guys following that? Beryllium, and then boron, 2p1. 1s2, 2s2, 2p1, and et cetera. Are you guys seeing the pattern?
2p2,
Well,
2p3.
actually, let me continue. Boron, carbon, nitrogen, oxygen, fluorine, neon, right?
2p6.
You notice something, every time we get, okay, this was helium, this is neon, and I know, because I know that every time we get to a noble gas, we've completed a shell. We're going to get to
Next noble gas.
3p6. That's going to be argon. The next one's going to be 4p6. That's going to be krypton. And then xenon will be 5p6. That's it's a pattern. But let's continue. So we got to neon. Sodium would be that. 3s1. So now we've done 3 of the elements in the first column. Let's look at that pattern. Hydrogen was, remember that was 1s1. What was lithium?
2s1.
1s2, 2s1, right? Remember that? And then we just saw sodium, which is 1s2, 2s2, 2p6, 3s1. So you see the pattern is that every element in that first column ends in something with s1. Has all the electrons before it, too. Exactly, that's the pattern. Rubidium 5s1, cesium 6s1, francium 7s1. You guys see that pattern? Yes. I'm getting applause. The second column. Okay, let's do one more. Sodium, magnesium will be here, right? 3s2. So now we've hit 2 of the elements in the second column. Beryllium, which is 4 electrons, was 1s1, 1s2, 2s2, right? We see now that magnesium is all this plus 3s2. And so, what do you think calcium will be? What will it end in, its electron configuration?
Neon.
4s2.
4s2,
You
yep.
see the pattern, right? Then strontium,
5s2.
5s2, barium 6s2, radium 7s.
He's talking about this one.
You see that?
Oh.
Now, okay, that's where they ended. They have everything else before them, right? So the complete electron configuration for magnesium is 1s2, 2s2, 2p6, 3s2. Okay? We continue doing it that way. You see that everything in the first column ends in S1, everything in the second column ends in S2. Now, the number before the S, the principal quantum number, the principal energy level, N, the way it's set up, beautiful. It's equal to the row number, right? In the first row, it's 1s1. Second row, it's 2s1. Third row, it's 3s1, and so on. Beryllium's in the second row, so it ends in 2. That's its row number, N, S2. Magnesium, 3s2. Calcium, 4s2, and so on. Because calcium's in the fourth row, for example. That one. We call those first two columns the S block because the last electron to go into any of the neutral atoms in that block goes into an S subshell. We skip transition elements. That we call that the D block, right? But we'll come back to that. And let's go over to boron. Boron has 5 electrons, so 1, 2, 3, 4, 5. That's just one of these two, right?
Or SP5?
No.
SP5. Or SP5.
That would be boron, right? And then, so it's 1s2, 2s2, 2p1. Do you see the pattern now? Can you predict what aluminum would be?
A what?
What would it end in?
A woman?
Aluminum.
Oh, they said a woman.
Right? It's going to end. It's in the third row, so it's going to end in 3, and it's right between boron, so it's going to be P1.
Could I swear I said a woman?
Gallium, B, 4p1, and so on. Have you guys seen that pattern? See, what I'm showing you here is how you don't need all that stuff if you have a periodic table. Yeah, they'll be P6, right? So as you go across the P block is that whole block from boron over to neon and everything beneath it, right?
Mhm.
Everything in the first column of the P block ends in P1. And what goes before the P is what the row number is. So for boron, it's 2p1, then aluminum 3p1, 4p1, etc. The second column ends in P2. Carbon is going to end in 2p2.
1 SP2.
You guys see that? And everything beneath it, 4p2, and so on.
Helium's just on.
So you're talking about going across or going down?
One.
I'm doing both.
Okay.
When I'm putting the number in front of the letter,
Completes the very first
2, 3,
SP.
4, that's going across. That's the row.
One
So
SP2.
the first row just has hydrogen and helium in it. The second row has lithium through neon in it.
So that's going to be
And that row number
1 is 2.
tells you what the N is. That's one. The number in front of the letter.
You get it now? And
Yeah,
then
yeah,
one
yeah.
is 2.
We still
2 is 2.
Are those numbers goldish? Are they the maximum number of electrons in a shell? And goldish, like you have 2 next to.
Oh, okay.
Yeah.
That's how many electrons
On
are
the subshell?
in that.
In the shell? 2
Total electrons. Notice 2 after helium and then 10 after neon is 8 plus 2.
What?
And then 18 of argon.
Call the dollar.
Argon's 18. See that?
You got the dollar. No, we'll go on with the story. What? See what, the gold?
Right, means you're shorter than this.
Dude, where's the gold at? Am I colorblind? What's gold?
I made
What's
this
gold?
way, I made
Where?
it that way. So,
Oh, that's just gases, isn't it?
What is the lithium electrolyte
I don't know, but
So, let's see if you guys can tell me what the complete electron configuration for sulfur is. Don't look in your book, because I know it has it written somewhere, right?
It does.
Just look at that periodic table.
3s2,
So let's
2p4.
start from the beginning, right? Start from the
3s2,
bottom. Start with 1s.
3s2, 3p4. 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 Final answer. 3s2, 3p4. That's it. 3p4. Final answer.
But then go back.
I'll start you out. 1s2.
Why neon? That's going forward from neon, but I want to go back.
2p6, 2p6, 2p6.
See how we're going through the periodic table?
2p6,
Past that, so it's 2p6.
3s2,
Then we're back to sodium and magnesium.
3s2, 3p4. Just do
Everybody
Rupuscus.
catch that? Any questions on how we did that just from looking at the periodic table? No? Okay, got it. What did I say? Obviously, you started using but that's okay. I assume you are. All right, so core notation, noble gas notation. This even gets kind of awkward, right? So we got more shorthand.
The cheating style.
Neon, bracket neon.
Core or noble gas notation. What is the electron configuration? Can you tell me from neon?
Neon?
1s2, 2s2,
2p6,
Yes.
2p6.
1s2, 2s, 1s2, 2s2, 2p6. That's neon, right?
Yes.
So what we do for our shorthand is
I trust
instead
you
of
will hold
writing
the
this
camera
out,
while you speak.
we just write neon.
Oh, just make sure he's
brackets,
son.
and that's what that
Make sure
means.
that there's there. Yes, so see that you don't, because I don't want white card. Oh.
This is core notation for the neutral sulfur. What you do, the way you write core notation is find the previous noble gas. Always go to the last noble gas, write its symbol in square brackets, and just fill in the electrons that come after that. For example, let's do core notation for calcium.
And S2.
So the first thing is to find the previous noble gas, which would be what? So we write argon in brackets, and remember, that stands for, that means all those electrons through argon. And then, what do we have to do? 4s2. That's the electron configuration using core notation or noble gas notation for calcium. So let's do a few transition elements for electron configuration.
Let's do some core notation.
We already did copper. Let's do manganese.
And then
Core notation. Okay. So previous noble gas would be argon. Let's see. 4s2 because we're past calcium. Then what?
3D5.
Good, it's 3D, right? I was going to see if you guys kind of figured that out. We're in the D block, okay? Which is when we get like to scantium and over, the something block. That's the D block. Because electrons now are going into the D subshell. The N, the number before the letter, is one less than the row number. That's because, if you remember when I wrote those arrows in that mnemonic, we went to 4s and then back to 3d and then to 4p. And the reason is it ends up that it's lower in energy to have electrons in the 4s before the 3d than it is the other way around. It ends up being just low. That's a lower energy state. So you go into the 4s first and then the 3d, right? Just like you said. So we're at 3d. Manganese, which column in that D block is manganese?
N? N is before you
Fifth
come to
one,
this
right?
part.
So that
N is
means
basically
3d5.
3d5, 1, 2,
You guys got that one?
C.
This is the way I write it. I write the order that the electrons go in. It's perfectly fine to flip these and write the 3d5 and 4s2. That doesn't matter. Exactly the same.
What if it has a negative or positive charge on the element? Next chapter. How soon?
We are or
Hold the breath.
It can be forming that bubble or any part of one.
Then it says excited state, what does it mean? Does it mean it has one electron?
Question I have is,
How many
An
electrons?
excited state, I believe I talked about this back when I was doing.
what was that? We was talking about how
An
periodic
excited
table
state
flows here
is
was
when, well, first of all, as opposed to a ground state. A ground state is an atom, all the electrons that are in that atom are in the lowest energy state they can be. An excited state just means that one or more of those electrons has been given some extra energy and is in a higher state. So we could write the electron configuration for an excited state. So these are all ground states. That's
That's
the
p orbital. And there's 6, 1, 2, 3, 4, 5, 6. Those are gas.
So let's do calcium.
This is your D element would be your
There are an infinite number of excited possible
your 10
excited states.
space.
It didn't state that was making me confused. It didn't state which excited state you're talking about.
There could be any. I mean, if they don't specify, you can pick any, right? The next lowest energy maybe. But to make an excited state like this, you take any of the electrons in here. Usually what we do is we take the last electrons that went in, rest, and we put them into another orbital that's higher up. An example of an infinite number of excited states.
This is 1s, 2s, 3s, 4, 5, 6, 7, right? Wait. See, I didn't show the orbital and everything. Why is zinc like that for 4s2? What's wrong
Well,
It's higher-
assuming I'm
higher
trying to
energy
get
sort of
confused,
electron configuration.
it could go higher. But that's an assumption that it's in the next highest orbital.
Because there's an infinite amount of orbitals.
Yeah, exactly.
So do you get it? Up higher. Any higher, right? Or I could have done.
Well, assuming, no, if
I
we're
could have
going to
done
exciting one electron, we are exciting one right now.
For the excited state, you release one.
Yeah, assuming how much energy you're putting into it. I'm not sure if you can.
That's an
You can ask
excited
him.
state.
Yeah.
Can you get it that high?
Can you take 2 electrons to excite out too?
Yeah, you can do that.
Example, please.
Multi-photon absorption.
You can put 4 as 0, dude.
I know.
How do you target just one electron?
By its energy.
Yeah, wavelength, by hitting it a certain wavelength.
With photons.
What? Yeah, we were talking about it like a while ago, like 2 chapters ago.
So,
Who's picking up?
now finish chapter 3, final.
Yay!
What? Why? I like this stuff. Go fast.
Chapter 4.
No, people do
What? Fun in lab. I have fun in lab. This guy also breaks.
And it seals your answers, I'm guessing.
I joined to pick up my brother on Friday night. Yeah, I'll pick up my brother too.
Oh, one thing I forgot from chapter 3, I promised you I would tell you which exceptions to memorize for the electron configurations. There's more than this, but these are the 4 that I want you to memorize. And those are already on chromium, copper, molybdenum, and
What about silver?
What?
You don't care for silver?
No. He doesn't like it.
I like silver, man. I'll give you copper for silver, bro.
No, bro.
Come on, bro.
No.
He doesn't like that stuff.
Silver's too damn good. I want gold.
yeah, that's pretty much.
Dying. I copy that. You're gonna need. That's on the test. It's on all the test. 3D5, bro.
And all of these exceptions are always, what do they call it? Paramagnetic?
Yeah. No. Yeah. Paramag. No.
They have to be always paramagnetic, because they would have one that's always empty.
Oh yeah, that's right. It's the first one, right?
No.
The 4S.
And there's a pattern here. Molybdenum is directly beneath chromium in the periodic table, and it has the same pattern in its electron configuration. Instead of being, if you just followed the order of filling like we've been doing for chromium, you would get argon 4s2 3d4. But just remember that its electron configuration is really argon 4s1 3d5. And the reason is basically the same as I was explaining earlier for copper. It's, we have 4s1 3d5, this is a half full subshell, and this is a half full subshell. It's just a little bit more stable that way. And then copper we've talked about. Molybdenum's just like chromium. We have a half full subshell and a half full subshell. Only it's 5s1 45, not 4s1 55. Because it's in the next row down. And silver is like copper. Half full subshell and a full subshell.
So is it usually if in the D block that if it can make it a half subshell or a full subshell, that's
D and F. We're going to stay away from the F block.
Okay.
Really, but, yeah.
Just curious from that. Why
In,
you need conclusion,
in
right?
the ground state of the neutral atoms, you don't see that in the nuclear elements.
I'm really confusion later.
Oh.
So memorize.
The valence electron, chapter 4.
Dude, why is this so easy?
That's why he's
Golden enzyme, but not functional. It gets functional. So I'm not asking you to remember golden.
Yeah.
All right, so you got that. Now, chapter 4. Valence electron.
Wait, on that one.
Now that we know about electron configuration, I can define valence electrons.
Should give you the book, man.
I only have like, what, 15 minutes?
Yeah, 20, bro.
Jack.
You know you love that lab book.
I know, I do like it. Only negatives is that.
Did I write my introduction for this one?
Hmm?
Did I have my introduction?
You,
I didn't write my introduction.
if you want, I think I have it written down somewhere on the side.
No, I don't. Fuck. Skip one. Oh no, there was no introduction for this one. That's right.
So, definition of valence electrons are valence electrons that have the highest occupied end in a given atom. So remember, N, it's the number in front of the letter, right? It's the principal energy level. 1, 2, 3. So the highest in nitrogen, the highest occupied end is N equals 2. So all electrons in nitrogen that have N equals 2 are valence electrons. So these two here have N equals 2. These three here have N equals 2. So a total of 5 valence electrons. I'm seeing some frowns out there. So is there something that's not clear about that?
Yeah.
Yeah. The definition of valence electrons. How we know which electrons are valence electrons, what we call valence electrons, and how many electrons in an atom are what we call valence electrons. It's really simple. You just look at N, the principal energy level, the number in front of the letters, and you find in the electron, you look at the electron configuration for that atom, and you find the highest N that has that's written that has electrons in it. And whatever that number is, the highest number. In this case, it's N equals 2. All the electrons that have that N are valence electrons. That's the definition. So that's right.
So it ended in 3D4 and 3's the highest one, did 4 valence electrons?
Yeah, well, I'll
That's
talk
just
about
nitrogen,
the
that's
block in a minute. But You have to look at it.
He's on nitrogen, isn't he?
But that's the
That's
idea.
nitrogen.
Yeah, that's nitrogen,
You
isn't
guys
it?
understand that definition?
The two's taken up, the three that's remaining. Is valence electron. I mean,
Let me ask
five
you this.
actually, not three.
We should do one more.
Phosphorus.
He would do
Okay, you
phosphorus.
guys help me out. Using core notation, tell me what the electron configuration for phosphorus is. I'll start you out with neon.
Dude, I can't copy this down right now.
3s2 3p3. Yay.
What's the highest occupied N in phosphorus?
5.
N equals 5?
Wait, what are you talking-
To the answer, right?
Oh.
Highest occupied N is this number here, N equals 3. And how many electrons have N equals 3 in phosphorus? 5. So there are 5 valence electrons.
This is so natural, it's just, you know.
Notice something. You see how phosphorus is right beneath nitrogen in the periodic table?
Yep.
They both have 5 valence electrons. How many valence electrons do you think arsenic has?
5.
5. It's the same column, right?
Yay.
Everything in that column has 5 valence electrons. So that gives you a shortcut, okay? For the, at least for the main group elements. Don't try this with the transition elements. I'll talk about those in a second. But everything in the first column, how many valence electrons do you think it has?
1,
Second column?
2.
I'm hearing different numbers.
You.
2, okay? That's how fun. So everything in the second column, remember, ends in S2, right? And
Yes.
that's going to be the highest occupied N, whatever that S is, right? 1s2, 2, or, yeah, 2s2, 3s2. So everything has 2 valence electrons. You guys okay with that?
Mm-hmm.
We'll skip the transition elements, go over to the P block, starting with boron.
4. Oh, sorry.
3, right? So boron has,
Let's
you
go
know,
to carbon.
helium, and then 2s2, 2p1. The highest occupied N is 2. There are 3 electrons there. The 2s, the 2 and the 2s and the 1 and 2p.
Nice.
So everything in that column has 3 valence electrons. Beneath carbon, 4.
4.
Nitrogen, 5. Oxygen, 6. Fluorine, 7. Now, when we get to noble gases, they're going to be all be 8 except for helium, right? Why doesn't helium have 8 valence electrons?
Because it only has 2
Because it
electrons.
only has 2, right? So it has 2 valence electrons. So that's a real quick way to just look at the periodic table and figure out how many valence electrons some neutral atom has. Transition elements. So we have some written up here. Let's look at that. In chromium, how many valence electrons do you think there are?
5.
5.
4.
4.
1, 5,
3. 2.
All right. So go back to the definition, right? The definition is the highest occupied N. In chromium,
Oh.
what's the highest occupied N?
4.
N equals 4. How many electrons in chromium have N equals 4?
1.
1. There's 1 valence electron in chromium. Is that? It's the definition. That's what valence electrons are.
Can we do another one?
Copper.
Man, shoot, a new metal.
1.
1 valence electron in copper. You guys see that?
Yeah.
Molybdenum.
1.
1. Silver.
1.
All right, let's do a different transition. Okay?
That's what I want.
What's the electron configuration for iron?
Iron.
Core notation.
Where's iron at? I can't find it.
Caffeine. In the middle, 26. 23, 6, 11.
I must be hella blind right now. I can't find it.
Is that right?
Copper. By manganese.
I might need
6 column
glasses.
over,
It's
right?
like kind of blurry.
So, what's the highest occupied N in iron?
4.
4.
How many electrons have N equals 4?
2.
2.
2. How many valence electrons?
2.
2.
2. Nickel. What's its electron configuration?
Oh, I get it now. Where's Kanaya?
And that has 2 over from iron.
So it'll be
Right? How many valence electrons does nickel have?
2.
That is safe to say, yes. The transition elements, most of them do have just 2 valence electrons. except for the exceptions. The only exceptions we're remembering are those four. Definitely there are other exceptions. Okay, so that's valence. The reason that we care about valence electrons in chemistry is that they're the highest occupied end.
So do all the exceptions only have one?
Until you get down to the F block.
I mean, out of the four you did.
Yes.
Yes.
Okay.
I hate transition middle. It's so uncool.
I love transition. They're easy. They don't have two accepted exceptions.
I know. That's what I said. I
Care
hate
about
them.
valence electrons, as I was saying, that in chemistry, okay, when we perform chemical reactions, and at the core of it, basically we're bringing atoms together and reacting. We'll talk about that later, but when two atoms come close to each other, the first thing we're going to see interact with each other is going to be the outside, which is going to be the electrons, and those are going to be the electrons that are the farthest out, right? The first things that come in contact will be the outermost electrons. And the outermost electrons are going to be the ones with the highest n, because that's what n tells you, is how far from the nucleus they can extend. And so the first electrons to interact, the electrons where almost all of the chemistry happens are the valence electrons. So it ends up being real important to know, which electrons are valence and how many there are. I think we'll end there too. Well, I don't know. At this point, I can't use sapling problems on the exam because you guys don't have access to them. And I have to make a decision now. I mean, yesterday actually I did. Because, you can't be changing stuff less than a week later from the exam. So, what I'm doing, the exam's still the same day. We can't push that back any further because then we just lose everything. The exam's going to be based only on the examples from class and the suggested homework problems. So it's not including sapling. As far as the points for sapling and due dates, don't worry about that. It depends on when they come back online, if they come back online, and all that stuff. But don't worry, you're not going to miss out on the points. It's not going to be overdue just because they were offline. I still have to wait and see what happens. When and if they come back online. But right now, the immediate concern is the test and how you're going to study for it. And so, as I said, what you should study for the test are now coming from two places: from my examples that I've done in class and from the suggested homework problems in the textbook. That brings up another issue, though. I purposely chose most of those suggested homework problems to be the ones that you don't have the answer in the back of the book to. Right? Because I was assuming you had sapling to bring you up to that point, because they are definitely a little bit more challenging than most of the sapling problems. And the idea was to bring you up to that point with sapling and then keep going with those. So, I mean, when you get to one, you're not sure what the answer is, ask me, I'll work it out with you. I don't have a solutions manual. I don't have an instructor's solutions manual. They didn't give it to me for some reason, so I can't make copies of the solutions or anything. But we'll just work them out together as we go through. But you guys understand how that's going to work.
When are your office hours again?
Every day, Monday through Friday, 8:30 to 9:30.
In the morning? So that's the only time you have
Discussions, Facebook. Last night I was having a discussion with Adam. Yes, he got irate with me.
No, I have my book.
Well, you know what? I looked at the same thing because I was watching as you guys were going, and I kept coming up with a different exponential. So
It was all about the exponent.
yeah, and well, I mean, there was a couple of things I saw what you had written down, and I was like, I totally skipped that, but I still got the same answer. So I don't know how I did that. So I don't know if I just did it in my head. I don't know, but
So that brings up kind of the strengths and the weaknesses of Facebook. One, just we were talking, but everybody else that looked could see it, and hopefully that maybe answered some questions. But it's also hard to put equations like that.
Yeah.
For rocks and all that stuff.
Right. But the thing is, like, it's hard to learn from my mistake if I don't know if I made the mistake or not.
Right, yeah, I mean.
And that's what a homework question's supposed to be.
Yeah, right.
And that's where sapling was great, because yeah, I got it wrong, but then I was able to figure out what I did wrong.
Do you know, where, there's a chemistry tutoring place, right?
There is a tutoring center. I'm
Yeah.
not sure about that.
And we do have chemistry tutors there.
There you go. So you work there?
Yeah, but he didn't show up twice. I had him twice and he wasn't there. Were you doing chemistry?
You're talking about
No?
tutors?
Yeah, no, the chemistry tutor. I was there twice and he skipped out. I was like,
Are you talking about Wu?
I don't know what his name was.
Hella smart, man.
Yeah.
He's too damn smart.
Yeah, I don't know what his name was, but
he sucks at
I was there
explaining.
twice, so I gave up.
You're all excited.
And then Tuesday's pretty much all day, so can you help
Next
show?
office hours in between now and then, I'll do that. Maybe, I'll figure something out and agree guys if we have more time.
Yeah, because most of us have class each night,
What happened? Last what?
morning class.
I have most of that class the rest of the day.
Usually they're like,
They're here by now.
there they are. Oh, there's mine.
Anyway, let's.
That's right behind you.
No.
They're talking about very. What is this asking?
No, I'm not going to record your day.